All right, let's get started. Today we have Chapter 9 on trees. Chapter 9 on trees. Let's see. Apple trees, banana trees. No, there's bananas growing trees. Cherry trees. Cherries growing trees. Apple tree. Apples grow on trees. Trees, actually, believe it or not, it's the same thing as a data structure in programming. So what I'm going to talk about today, well, what are these trees? Defining the trees. Different types of apple trees and banana trees as data structures. Defining the terms associated with trees. So there's a lot of definitions. This is 86 slides of definitions. I don't think we're going to get through all of it today. We'll probably hit half of it, maybe, hopefully. We'll see how far it goes. It depends on how interesting the trees are. Defining the trees. Discussing possible implementations of trees. And analyzing the tree implementations of collections. So we have built-in collections, part of the Java APIs that we're going to look at in terms of the trees themselves. Probably not going to get to that today. I'll have the examples next time, I believe. Discussing methods for traversing trees. Examining binary tree examples. So binary trees are probably going to be the most effective tree, just like binary searches are the most effective type of searching. And when I say effective, I mean it's efficient. That is, it doesn't take as much time as some of the other algorithms that are pretty much doing the same thing. Interesting concept is we can have the same kind of structure built in hundreds of different ways. Some of the building of the structures are efficient, some of them aren't. So it really depends on what we're considering in terms of the architecture of the system, in terms of how making it efficient. And how are we measuring the efficiency of it is how fast it takes to find something in the tree. So just like we used lists and different types of lists to create, a collection, a tree is also a collection, but it's sorted differently or represented differently. Maybe that's a better way of doing it, saying it. So a tree is not a linear structure. It's a nonlinear structure. It's defined by the concept of the node, and we have nodes in the trees. All right, you can call them nodes. Don't call them branches because we can put nodes in branches. And there's a hierarchy to the nodes that we're defining. Other than the first node, which is the root node, everything else is exactly one parent to it. So think of it kind of sort of like a list, but it's a collection of sublists that are put together. And the concept of we looked at before the linked list that had nodes, it's the same kind of node. We're just going to link them differently. So it sounds like a huge concept, but trees really aren't any different than linked lists. Because we're defining nodes and we're putting the nodes together, but instead of putting them together in a linear fashion, we're doing it non-linearly. So for trees, the operations are dependent upon the type of tree. So some trees, we have different ways of navigating it. So the way we build the tree determines how we're going to traverse it. And to traverse it, travel through the branches, travel through from node to node, we essentially get from root nodes to leaf nodes. Leaf nodes are the end nodes. So if you imagine a tree in nature, what is on the end of the tree are the leaves. Those are the terminal points in the tree, or the end nodes. So they're the leaves. So we travel from the base through the trunk all the way up to the top of the tree, and we can go out each one of the branches, and eventually we're going to end at the leaf. And the interesting thing is that abstractly, it really does follow the whole nature concept of trees, which is kind of fun. So here's some more definitions. In order to discuss trees, we must actually look at and first have common vocabulary, which is the purpose of today, is to give you the vocabulary that we're working with. So we have already introduced a couple of terms already, as I mentioned in the beginning of this slide set, the node as a concept and the root. The root is the starting point. It refers to the base of the tree or to the node in the tree that does not have a parent. In a real tree, we don't have roots. You can think of them as the roots in the ground of a real tree. But in a tree structure, in nature, we have different parts, physical parts. We have the trunk, the roots, the branches, the leaves. In a computer science tree, all we have are nodes. Everything's a node. And all the nodes have different names. So all the pieces represent different components, but they're all the same structure, physical structure that's created. which is interesting because I have read through some articles and I have seen some examples of trees created more abstractly using different types of components, where the nodes were kind of equal in terms of their object existence, but they carried on different roles and they had different sub-objects contained in them. And that is what I would call a more sophisticated version of this concrete data structure. But from a theoretical point of view, the base of the definition of the tree involves nodes. Nodes refer to the location in the tree where the elements are going to be stored. And we have a root node, and then we have a leaf node, which is the beginning of the tree and the end of the tree. So each node in the tree points to other nodes, so to the node that are directly beneath in the tree. So the hierarchy starts at the root and goes to the end. If you turn the tree upside down, you've got the structure. It usually is built from top to down, where abstractly thinking about nature is really bottom up. How you build the tree doesn't matter, as long as the way you build the tree is how you're going to read the tree. So in terms of computer science and programming language concepts and compiler design, we have what's called abstract syntax trees, where we take a grammar, we apply it to sentence structure, we parse some source code from a high level, C code as an example. We take the C code, we break it out into lexicons, and take those lexemes, we take them and define what they are, and we build a tree out of this. And this is called an abstract syntax tree. And the tree represents this language. It represents what's been spoken or what's been written in terms of the program commands and the statements that are in the program, in the source code. And we read the tree to get the meaning. It takes the syntax and turns it into the semantics, which is the meaning of the syntax. The tree provides the structure when we read it to understand what it is we're doing. We're assigning values, we're removing data, we're sorting it somehow. And the meaning only makes sense if the tree is read the right way. So abstract syntax trees can be written from top down, bottom up, left, right, left. Depending upon how you're building it, that's going to determine how you're reading it. So there's no real generic structure to a tree that can apply towards all trees. Trees themselves as a data concept or as a data structure concept are unique. And so it's not like a list is a list is a list. Well, actually they aren't. A queue is different from a stack. So every one of these trees is unique in itself, although they all talk about nodes and they'll talk about roots. They'll talk about children. So the nodes that are beneath the root node, every other node is referred to as a child node. So we have a parent and we have a child, and we have a parent and we have a child, and a child can be a parent can be a child. Everything except for the root. The root can't be a child, the root's always a parent. So the child of the child is then called a grandchild. And a child of a grandchild is a great-grandchild. Well, there's a hierarchy to it, because you need to know where it falls in the order. So a node that does not have at least one child is called a leaf. So that's the leaf node. Nobody really memorizes the definitions of all these things. Just know that the leaves are at the end of the tree. Well, I shouldn't say that. Sometimes you see leaves growing on the base of the trunk. Those are trees that need to be trimmed. They're not trimmed properly. But a properly trimmed tree, the leaves are at the end of the branches. So a node that is not the root and has at least one child is called an internal node. In the real world, that would be a branch. So it's not the root, and but it has at least one child, and usually has more than one child. So it's an internal node, aka branch. We don't call them branches, we just have internal nodes, but it really is representing the same concept. Because branches can have other, and this would be a branch actually. This would be a branch, that would be a branch, or internal. Get my terminology. Internal node on the inside. These would be internal nodes. So here's our root A, and we have here's an internal node here. Our internal nodes, and because they're not representing root, but they're actually acting as a root. So here's our leaves at the end. Anything at the end is going to be a leaf node. So we can take complex information, structure it out in this format, and derive meaning from it. It can solve questions for us. As an example, one of the most popular things that trees are applied to is mapping problems, such as not an efficient way of solving the traveling salesperson problem, but traveling salesperson problem says we start at A, we need to get to P as an example, and the tree represents all of the different routes we could possibly take, to get from A to P. Which route's going to be the most efficient? Looking at this, I would probably go this way. With kind of the direct line. If I went this way, and maybe this one came back up this way, and that would be a little slower route. But we could possibly come out with, hundreds of different, not in this particular aspect, but there's only one route really. There's only one way you can go, you can't go to C. We could take all of the different sub-routes of the internal nodes and treat them as calculations as well. You can come up with essentially an entire list of possible answers, solutions, and then find which one's going to be the shortest by doing a calculation on it, which is how a lot of problem solving is done. So other types of data structures in computer science, such as lists and other types of containers, queues, stacks, are normally done for processing information, for sorting it. We can do it for searching as well. We can find information in it. Trees are unique because they add the component of problem solving. We can make decisions based upon the trees, where we can't make a decision normally based upon a list of items. We could decide how to divide the list out. But, as an example, if this were applied towards a business setting, this could be a critical path method. This could be showing us all of the ways that we could possibly schedule our work for a project and calculate each one of the different paths. We can come out with which one is going to complete our project in a short amount of time, which is really the critical path method applied towards project management in a business setting, where the tree structure from a computer science perspective is solving the problem for us. So it gives us the information, it helps us understand the information a little bit better, and solves the problem. We don't get that out of a list, even if we search the list. It's in there, it's not in there. Here it is, here's not here, It's more for data organization versus problem solving. And just in the case of, I mentioned earlier, in terms of compiler design and creating an abstract syntax tree, it tells us what the syntax we wrote, what those lines of code meant, and then that way we can convert it into assembly language, or we can take it and use it for some informative reason inside of the compiler. Any node below another node and on the path from the node is a descendant of that node. So if it's on the same path, it's just like kids, parents, your descendants, and they have parents and the grandparents all the way up the route. And they're descendants on one line, but they're not descendants on the other. So any node above another node on a connecting path from the root to that node is called the ancestor. The ancestors are before, just like life. Any children on the same, or siblings, they all come from the same nodes originally, from the same path. They have the same descendants and they have the same ancestors. So a tree that limits each node to no more than n number of children is called an n-array tree. You'll see this a lot in literature. You'll see it in examples. You'll say, this is an n-array. And people go, oh no, what is that? I've never heard of that before. Nothing more than a tree that each node is no more than 1 or 2 or 3 children. It means it's limited. Why do we do that? Well, that way it gives us a better way of organizing the data to reduce the search space. If it's limited, it only goes to a certain depth, we can create what's called a balanced tree, where each one of the descendants has the same number of nodes. We fill the nodes up, and then we know, and we can build abstraction from that and use it for different problem solving purposes. Makes the tree more manageable in the n-array. And so n-arrays, you set the n pretty high, you're not going to run into a situation where you can't represent it, but you're going to fill up another node. So it's an example. You have students and you're assigning them to TAs, and you're going to create a tree structure out of it, and there's a limit on 30 students per TA or something. You're going to build the trees, and then it's going to be an n-array situation, and you're going to be able to tell which ones are assigned to which TAs depending upon the ancestors, and which ones are descendants, which ones are assistant TAs of the TAs, and stuff like that. So the n-array is good for creating a balanced tree, and we'll get to an example of that further on. Each node in the tree is at a specific level or depth within the tree. the nodes don't normally change. The position in the tree and the position of the node that we're looking at can change, but the nodes don't normally change. So unlike sorting and searching and the stacks and the queues, the items in a stack always change. The items in the queue are sometimes changing or being positioned. We're moving and we're inserting and we're deleting. We can still insert into a tree, but once we insert, the tree pretty much grows around itself. And the nodes are going to stay in their position. We can move a node and reposition it, but it's not something that we're commonly doing to the data structure when we're working with it. Instead, we're reading the data structure. So it's built once, read a lot of times. Or a queue, a stack, built constantly. Popped on, popped off, popped on, popped off. The usage is a little bit different in terms of its operations. We're primarily interested in the path. So the next point being that the path length is determined by counting the number of links that must be followed to get from the root to the node. That's how long or the distance of the path. And the path length is something that's called upon and used a lot in terms of the structure. So the root is considered to be at level 0. The children of the root are at level 1. The grandchildren of the root are at level 2. So the numbers get bigger, the levels get bigger. So if you start out with 0 as the root and you move everything down, you end up with bigger numbers, higher ordered numbers at the leaves. So the leaves are always the highest numbers, the root's always 0 or 1, depending upon how the people like to count. The height or the order of the tree is the length of the longest path from the root to the leaf. So if we're not running an NRA, if we're not fixing the tree to a certain end length, and we're just making it essentially grow unlimited, then we can calculate the order, and the order is the length of the longest path, and that would be the longest traversal through. Thus the height of an order of a tree in the next slide is going to be 3. But take a look at the next slide and come back to this in a second. We've got 0, 1, 2, 3. So we're looking at a 3 height in terms of the level. So because we always started ground 0 is the roots. So if you want to consider it in terms of the level instead of the ordering, this would be all in the same level. And we're interested in finding the same level because we can interpret the solutions to problems by traversing to a certain level and then going across left or right from that level to come out with alternative solutions for certain things. Let me go back to the slide because I wasn't quite done with it yet. The path from the root A to root F is of length 3. So A to F is 0, 1, 2, 3. That's the path we're looking at. So to D would be 2. And the path from A to C is of length 1. A to C is just 1. And this is not a balanced tree. When I use the word balanced, it means that it's left heavy. We never say left heavy, but we usually say balanced or unbalanced. So we know that this is not going to take as long to search as this part. So if we have an order to it, we could possibly figure out ahead of time which might be the easiest way of searching it. So it determines how we're going to read the tree. Unbalanced because it's, heavier on one side than it is on the other. Just like nature, we get trees that aren't balanced properly. They're growing on one side. Something. Just to say that plants, actually, it's a good experiment. Actually, plants and trees, they grow towards the sunlight. So if you put a tree in your house, you're not getting a house tree, a small little tree. Well, Christmas is coming up, but it doesn't matter. That's not growing. That's dead. You put dead trees in your house for that. You put a live plant, you put a live tree in, you put it in a corner, let's say, for example. Hello. And you open up the window and let it sit there for a couple years, or maybe 6 months, maybe a year. You'll notice it actually grows. So it sort of looks like it'll grow in one direction versus growing evenly or being balanced. So kind of an interesting way of considering what would be balanced in terms of the tree structure. And there's reasons why you'd want it balanced in the long run. And we'll get to that eventually. So in terms of continuing with our definitions, the tree is also considered to be balanced if all of the leaves in the trees are roughly the same depth. So that tree is unbalanced, obviously. So, actually, going back to my Christmas comment, a lot of people like unbalanced trees, or they cut them to be unbalanced. Because you know what, the tree might not fit against the wall, it might not fit in the corner. So you cut it so it's unbalanced. So. But there's a utility for it being balanced, because you could turn it around if you wanted to. So can't see the backside, cut it away. Not going to see it. But if you had a search problem and the tree wasn't balanced, it might throw off your algorithm. It might give you a different algorithm implementation to search that tree. So while the use of the term roughly may not be intellectually satisfying, the actual definition is dependent upon the algorithm being used. So trying to bring this around to the concept of algorithms and how those algorithms could be used. Depends on the shape of the tree. It depends, again, on the nature of the problem that you're trying to solve. So in other list structures, we always search it the same way. We always start at the beginning of the list and we go linearly. Or we do a binary search, we start in the middle, we split it in half, as we talked about a couple weeks ago. Or we do a bubble sort, or we sort it and search it consistently. With trees, it's kind of different. We can customize the search and the sort because we have a unique structure. No tree in nature looks the same, actually. No tree in computer science is really going to always look the same either. It's always going to come out a little bit differently. So there's a lot more flexibility, and that's why a lot of people like the tree concept, like the data structure concept versus the strict list or collection kind of concept. Some algorithms define balanced as all of the leaves being at level h, or h minus 1, where h is the height of the tree, and where h is log n to the n, where for an n array tree, that means if we were going to limit it to like 3 branches, or limit the concept. So you might look at this and go, well, this one on the left is balanced and the one on the right is unbalanced. And the interesting thing is you're going, well, this one was this is where the light source is over here. All the growth on a tree actually grows towards light. It's true, I've experimented with this, actually. You can create an unbalanced plant by having the window open over here, and then keep this rest of it dark over here, and the whole tree will grow out the window. Seriously. In fact, people do this in their yards too. Okay, this is the last time I'll go off on this tangent, but you ever seen plastic bags, garbage bags, over like certain parts of like ivy? It's because it's too heavy. They're trying to fill it out. So the ivy will grow out of the plastic, and it'll actually, if you have like a big piece of fence, let's say for example, and you're trying to cover the fence with ivy, and you plant it and it's growing up, right? It's all going to be concentrated where the light source is. So this piece over here that's in the shade isn't going to get any ivy on it. So all your ivy is going to be growing this way, right? So you put a plastic bag over the ivy that's growing healthy. It's not going to hurt. The bag's not going to hurt it, but it's going to force it to get away from the bag. So you see those fences, and people that do this manicuring of their gardens and everything, they love to use black garbage bags. You put it over, and the plant will run away from it. It will try to come out the sides. So you're forcing it to grow evenly and balance it over. Just like on the fence, it's going to the same level. So it's always going out to 0, 1, 2. Although we're missing, we only have one of them over here. This is still balanced, believe it or not, by definition, if it's all going out to the same level. So it's all making it past a certain area, and it's complete in terms of its level balance. This is unbalanced because we have 0, 1, and we have 0, 1, 2, 3. If we were creating an array to sort through these nodes, we're going to waste time. We have to go all the way through 3, and we'll only have 2 in this node. So it creates a situation where it's not so efficient. This, we always have 3. So if, I is equal to 0, I is less than 4, we can actually productively go through the entire tree on each branch. And this one here is only 2, but the left and the right hand side of the tree is balanced. So the concept of a complete tree is related to the balance of the tree. So a tree is considered complete if it is balanced, and all of the leaves at the level H are on the left side of the tree. So we're looking at the left side of the tree, and all of them are complete. So while a seemingly arbitrary concept as well discussed in, well, I'm going to talk about this later when I talk about B-trees actually. The definition has implications on how the tree is stored and certain limitations. So we usually look for the left side. So on the left side of the tree, it's kind of an arbitrary way of balancing it, but so if all the leaves are at the H level, then we're balanced. So tree A and B on the next slide are complete, while tree B is not. A and B is complete, but C is not complete because we're at the H level on A and B. So some complete trees. Just here's our H definition, because I know some of you probably are wondering what does that mean again. Some algorithms are defined or balanced as all of the leads as being at the level H or H minus 1, where H is the height of the tree. So the height of the tree, if all of the leaves are at the same height. And the height of this tree over here, the height of that tree, they are of all the same, but on the left-hand side. So meaning A and C on the next slide are complete. Well, excuse me, B is not complete. A and C are complete. Let me rephrase that. This one is the incomplete one. They're all at the same height, is what I'm trying to say. So these are all at the same height in terms of this. These guys only one, and here we have 1, 2, 3, 1, 2, 3, and it's starting on the end. Because it's on the left side arbitrarily, we're saying that this is complete. It could be on the right. And this is, we would have to add 1, 2 more on here to make that complete. So, not to confuse you even further. It's like pointing out the wrong example. But yeah, note to self, B is incomplete. C is complete. Implementing trees with links. So let's talk about the nodes and the links. So while it's not possible to discuss the details of an implementation of a tree without defining the type of tree that we're going to use, because each one of the types of implementations are slightly different, we can look at the generic strategies here of implementing it. Most obvious implementation is a linked structure. So a linked list, in terms of its implementation, works with the node concept. We take the nodes that would be normally part of a linked list. We extend the concept, so instead of doing like a singly, which is keeping track of next, or doubly, which is a next and a previous, and we have this linear kind of organization of the nodes. Each node would be defined as a tree node class, as we did with the linear node class for linked lists, and we would define different properties for the nodes to keep track of the link structure depending upon the type of link structure that we were creating. So each node would contain a pointer to the element to be stored in the node, as well as the pointers to each of the possible children of the nodes. So you might be thinking, well, what do you mean? Well, you know what? We just actually built a linear structure all over again. Except for the linear structure isn't going from left to right anymore. It's going left, right, up, and down. So we take the same node concept from a singly to a doubly, and we add it to a tree concept. We have left, right, up, down in terms of concept. Then we can keep track of all the things that are connected to us. And we can keep track of children and parents and siblings on the left and right. So depending upon the implementation, it may be also useful to store a pointer for each one of the nodes to its parent. So, and if you get the concept, it only needs to know about its parent, and its parent knows about its parent, and its parent knows about its parent. So each node only needs to keep track of 4 pieces of information at maximum. Depending upon the implementation, we don't need to keep track of everything. We just need to keep track of what it is we're interested in looking at or traversing. So we could use arrays for it. So the implementation of trees with arrays for certain types of trees, binary trees as an example, and we haven't talked about those yet, but we'll get into that. Computational strategy can be used to storing a tree using an array. So we create an array structure, and in the structure we're keeping the position. So for any elements stored in the position n of the array, the element's left child would be stored in position n. Into the second plus 1, elements to the right are going to be in the right position. In the second plus 1 plus n plus 1, which moves it over 1 to the right. So strategy can be, what we're doing is we're just keeping track of all the n's essentially in terms of the position. We're just using an array to keep track of the nodes or the positions. So the strategy can be managed in terms of the capacity in which the same way that we did for the array-based collection, it's fixed. We only have so many numbers that we're going to be storing. Despite conceptual elegance of the solution, it is not without its drawbacks. It's easy. In fact, using arrays is quite simple for most data structures. As an example of one of the drawbacks, if the tree that we're storing is not complete or relatively complete, we might be wasting a large amount of memory allocated to the array and the positions of the tree that don't contain data. If you think of it, it's the same problem you have with a list. If the list is able to hold 50 items but you only have 25, and you create the array for 50, you're wasting data. So if the tree is not complete, you're going to be wasting some data in terms of the elements. And here's how it sort of works. So the numbers on the bottom are the index values of the array. We create the array. And we say for 0 through 7, which is going to be the depth, the height of the tree. In our case, it's going to be 7. 0 is going to be the root, and the root is going to be A. Number 1 is going to be B, and number 2 is going to be C. And, we got D, E. Well, we don't have anything over here. F is down here, but we're missing these two next to D and E. We're missing the two components. So this is why it would be sort of inefficient if we were missing a lot, if the tree wasn't balanced. Another thing to note is this was reading from right to left in the array, which is a decision that we have to make in terms of the implementation. There's no law that says we have to go right to left. In fact, there's a lot of people that read it left to right. We can go right to left if we want to. And it's just the order in which you're putting it in. Interesting thing is the same thing done with most tree structures in terms of the data structure. Do you write it at the beginning of the list? Do you write it at the end of the list? Are you reading it from left to right or right to left? How you're building the tree is probably going to be how you're going to, essentially the logic you're going to use when you're recreating the tree or storing the tree information. But as you can possibly see as another side comment, this particular tree that doesn't look too linear is linear, if you think about it. So it can be searched in a linear type of fashion as well. So although it doesn't look linear, it can be represented in an array or in a linked list structure in a linear fashion. So another note to actually make about this is keeping it stored in an array concept is limited in terms of the amount of information. This is holding the position that's associated with the elements of the tree. No other data is really being stored. If you wanted to extend the concept out a little bit more and make it a little bit more sophisticated, you could, as an example, store nodes in here that are of a class or a structure implementation instead of, let's say, integer values. So this could be an array of structures or array of classes. And these instances that were populated in each one of the index values could be storing a lot more information. One problem with that is it's very memory intense, and what if you're not going to use all that information? So the purpose of the implementation of the array should be dependent upon its use. So if you're not going to use it, if you just care about the positions, then just use the positions. So that also is another side comment. Last thing I'll say on it is that a little bit harder to read this, especially, well, you'd have to substitute and put 0 and 0 in there, but if you're searching for something in here, you almost have to pull the elements out abstractly, recreate this in order to actually, figure out that C doesn't have any. Because how are you going to know that C is the, you have A, B, C. If you've taken this, flatten it out, and put it into an array content, how do you know that D is over here and that D is not over here? So it's the meaning that's associated with the rules of building the tree and traversing the tree that are going to give you that. Structure is not going to give you that. So there's a likelihood and definitely a potential of there being some errors in terms of how that array is being used. It's an array of arbitrary numbers, not very self-identifiable. It's not really telling you anything. So implementing the trees and arrays to continue along with the example, a second possible array implementation of a tree is modeled after the way the operating system manages memory. So instead of assigning elements to the tree in the array position by locating it in the tree, the array positions are located contiguously on a first-come, first-served type of basis. and you're populating the elements in the array by sort of a memory management kind of allocation. Each node of the array will be a node class similar to the tree node class that we looked at earlier. But instead of storing the object reference variables, as we looked at before, as pointers to its children and perhaps to its parents as well, each node would store an array index of each child. So we're storing an index in the array component instead of just a number, a single number. Because if we have the items stored in the index values and they're self-identifiable and they're containing the information that they need, we don't have to search the array. It doesn't matter what position in the array they're actually stored in. Because that's one of the advantages of being able to have the array actually, the elements in the array actually identify themselves. So the approach allows elements to be stored continuously in the array so that space is not wasted. So we're not looking at position, instead we're looking at content. So the approach increases the overhead of the deleting elements, and same thing we get with lists actually. In the tree, since either remaining elements have to be shifted over to maintain the continuity, or the free list has to be maintained. So here's the other thing: you leave the holes and create a free list. The computational problem of creating the free list is going to essentially build into this, take away from some of the algorithm efficiency that you might have otherwise. So, or don't leave the holes, essentially. So here's a simulated link strategy for arrays that are implemented in terms of the tree. We have A, and the position is 2 and 1. We're going from 1 to 2. C has no children. A has 2. So you can kind of say C is empty. B has 2, 4 and 3. E's got nothing. So D's got F, only one F. F has got nothing. So you might look at this and go, well, you know what? There's more holes in here. But these are single. These would be single elements that would be stored. So what we're doing is basically capturing the child nodes with the parent nodes and storing the information together associated with the parents and then putting all the parents out. Because everybody's a child is a parent all the way out to the leaf. But this F could possibly be a parent, so it's got a space right here. And then we read this structure and we go, oh, okay. So this index value belongs to this one. And again, the same thing as before, these are the leaf nodes up here, and this is the array on the bottom. This is index 0, 1, 2, 3, 4, 5, all the way to the end. So I think it's a little bit more complicated, actually. But in theory, it allows you to save space in the array, allocate contiguously. So in the analysis of the trees are useful for efficient ways of implementing other types of collections. So in our analysis, the list implementation in Chapter 6 described the find operation as expected of the expected case n divided by 2, or O to the n, which is kind of okay in terms of its efficiency. If we implemented an ordered list using a balanced binary search tree, which we're going to see next, the binary search tree would be added property of the left child is always less than the parent, which is always less than equal to the right child in terms of the balance. Then it would be an improvement upon the efficiency. So people use trees, long story short, especially binary trees, because the efficiency of the search algorithm is much faster. It's not a matter of having to go through all elements. Well, actually, this is going to tell you why as well. So, it's due to the fact that the height of the order of each tree will always be log n to the second, to the n, where n is the number of elements in the tree. If you fix the tree elements, you know the depth, and so the depth can be done a little bit more optimally than doing a search through the entire tree one item at a time, in terms of a linear or even a binary, similar to discussed in terms of the binary search. So, same concept actually applies, except for the search depth is smaller. It's to the n, which is not going to be as big as the entire structure. So, in layman's terms, the tree is efficient because if we know if we know C is right here, we don't have to go all the way through here to find C. We know it's here. So it's a shorter path, essentially, on this just particular branch. We can easily say there's nothing underneath C. C is the starting point. In a list, if this was a straight line and we were considering a sort to find C, it's going to take us longer to find it if we have to go through all of the elements without the order being considered in terms of the length of the branches. And our depth search space from here is 0, 1, 2, 3. It's only 4 levels deep, or 3 levels deep actually, because you don't really count the root level when counting. So 3, instead of, if this were wide, it would be a lot longer. If we were to take all this and flatten it out, the search space is much longer. So the concept is you branch it out according to the logic that you're searching. So you're separating out the search paths into A, B, C, D, E, F, G. And this could be people who are taking this class, people who are taking this class, people who are taking that class. So it's similar to a binary search where you're getting at the group that you're interested in finding it in and is highly likely present in that particular group. You're finding it a lot easier, and the path to be searched is a lot shorter. So the balanced n array tree with n elements, the tree height will be log n to the n. So with added order, and basically meaning telling you it's a smaller search space. So the added ordering property of the binary search, you're guaranteed to at worst search one path from the root to the leaf. Not so bad, actually, at the worst case scenario. So the information I've been talking about so far is related to a generic tree concept. We haven't seen the tree implementation yet in any of the different techniques. But along with that comes a generic concept of traversing the tree, as I mentioned before. So we have tree traversals to think about, which is equivalent to saying we're searching a list. When you traverse the tree is another word for searching. We're trying to find something. But it's not really the concept of searching, which is why it's not called searching. Searching, we're trying to find something. Traversing, we're trying to read it, and we might read the whole thing to understand something. And the understanding might be the solution to a problem. So there's 4 different basic algorithms that are associated with traversing the tree, and they're used to apply towards different problem-solving techniques. So we have more flexibility, as I mentioned earlier. When a search is not just a search. It's not a generic concept, it's a traversal. We have our pre-order traversal, where it always reads through it the same way. We have an in-order traversal. We have a post-order traversal, and then a level order traversal. Level order traversal is more what you get with databases. A database can be implemented in a tree. You can think about the concept. And the row would be the level. Once it found the record and it found the row, you're at the same level, you're going through and you're finding fields of the same record. Post-order and order are telling you which order, which direction you're going, and the pre-order is just going to be preset ahead of time. It doesn't really matter what's in the tree, it's always going to do it the same way. So let's take a look at them in a little bit more detail so we can kind of analyze the differences between the two, all of them. Pre-order traversal is accomplished by visiting each node, followed by its children starting with the root. Every single piece in that tree is going to be touched. We're going to see it all. We need to see it all when we have to take in all of the data. Given the complete binary tree, on the next slide, we've got a pre-order traversal that's produced in the order of A, B, D, E, and C. We know ahead of time, this is how we're going to do it. We're going to go A, B, D, E, C. We go A, B, D, E, C. This would be top, down, left, right. Essentially is what this categorized as. Because we start at the top, we don't have to. We could pre-order it. Well, we could pre-order it top, down, right to left. If we did that, we go A, C, B, E, D. So if we were coming up with program language syntax as an example, and it was 1 plus 1 plus 1 equals something, and we went 1, and we had, oh no, answer is equal to I plus A or something, we would add them in the reverse order if we were accumulating the data. We would actually get it backwards if we wrote it this way and we read it this way, which is going back to my point of when we developed a tree, we develop it for the way that we're going to traverse it so that the information makes logical sense. So the pre-order, stated in pseudocode, the algorithm for the pre-order of the tree is visit each node, visit the node, traverse left child, traverse right child. So left child, left to right. An in-order traversal is accomplished by visiting the left child of the node, then the node, then any remaining nodes starting with the root. So the in-order traversal, the next slide here, is going to be produced by D, B, E, A, C. Whoops, it's not in here. Okay, that's okay. Well, if you go in D, B, now C, well, it's not written correctly. Okay. So an in-order traversal from the previous tree produced would be D, B, E, A, C. Actually, it is in there. D, B, E, A, C. D, B, E, A, C. Hello. Current node. So it's going this way. D, B, E, A, C. Which is different than top, down, left, or right. Left child to the node, right child to the node. So in-order traversal, stating a pseudocode, the algorithm for the in-order traversal of a binary tree is, and when we get binary tree, it's like 2 nodes go to 1 node, 2 nodes, 2 node, 2 node. So we have binary being 2. Traverses the left child, visit the node, right child. So left child, visit the node, right child. Post-order traversal, accomplished by visiting the child, then the node starting with the root. So given the same tree in the post-order traversal, produced the following order: D, E, B, C, A, D, E, B, C, A. I gotta go back. D, E, B, C, A. D, E, B, C, A. So this is bottom up, post order. So instead of a pre-order top down, it's a post order. D, E, B, C, A, bottom up. And you'll see in the literature, top down, bottom up, instead of seeing all of these other different ways of describing it. But the concepts are all the same. They're universal concepts. They're just given different vocabulary. So post is after. Post order would be bottom up. And if you were to take a look at the pseudocode that was associated with this post order traversal of the tree, it would be a left child, right child, visit node, left child, right child. Always going left to right. So. Or we have the level order. And we can do the level order from bottom up or top down, depending upon how we want to do it. Level order traversal is accomplished by visiting all of the nodes at each one of the levels one at a time, starting with the root. So traditionally it does start with the root. Given the same order, a level node would be A, B, C, D, E, which is going to be essentially order node or level node. So I don't have to go back to that slide, do I? No. Start at the top and go down, level by level. So, which is kind of like how the traditional level, in terms of the list, is actually built. If you think about building the tree, you usually start A, B, C, D, E. So you go down one level to another level. So. Alright, stated in pseudocode, the algorithm for the level order traversal for the binary tree would look something like this. I'm going to create a queue called nodes, maybe. Create an unordered list called results. Enqueue the root into the node queue. While node queue is not empty, dequeue the first element from the queue. The element is not null. Add the element to the rear of the results list. Enqueue the child of the element of the node queue. Now let's add a queue as a result list. Enter an iterator. Return an iterator for the results list that might be obtained from that. So I also often wonder why why you would actually build it that way, essentially, because it's actually kind of upside down if you think of the concept of a tree. But most people think to put the root at the top. I don't know why. Maybe I'm the only person who thinks about putting the root at the bottom and building it up. Because when I build my trees, I do it in the opposite order. I start the root down and I build up in the upward direction instead of the downward direction. So, interesting. I guess it depends on whether you're a left brain or a right brain kind of person. Maybe that should be a computer science thing, test. Which way do you build your trees? Which way do you add to your stacks or your queues? You add to the beginning of the list or the end of the list? That's usually by problem definition. That's the straight answer. So, implementing a binary tree. So let's take a look at binary tree. For example, as possible implementations of trees, let's explore the simple implementation of a binary tree. The name sort of gives it away. Having specified that we're implementing a binary tree, we can implement a set of possible operations that would be common for all binary trees. Looking at other than the constructors, none of the operations add any elements to the tree. We'll take a look at the possible class implementation for it. It's not possible to define an operation to add an element to the tree until we know how the tree is going to be used. So as I mentioned before, you can't just arbitrarily create a tree unless you know how you're going to traverse the tree, which is kind of weird. Think about it. It's almost like in other types of data structures, you figure out what you're going to store, what are you going to store it in, and then you build the program to work with how you stored it. So if you built it in a queue, you have operations that are going to work on that queue. The interesting thing about trees is like you have to think ahead of time, how am I going to use it, and then build the structure so that you can use it in its intended purpose. So here's some basic operations that would be part of an implementation of a binary tree. We would have a get root. We have to always find a root. In fact, we're going to have get root in every tree implementation. We're going to need to see if it's empty. Is it empty? The size. Does it contain something? Can we find a string? Maybe a toString method to convert integer to a string. Maybe an iterator in order, an iterator for pre-order, iterator post-order, an iterator for level order. And these iterators would be sort of like the loop that would start and go through the nodes and the kind of the order in which it was, in order, post order, all those little techniques we just went over. These are sort of generic for all trees, however, not just for the binary tree. Here's our UML diagram if we were to create one. It had a binary tree abstract data type interface. The interface has all these methods associated with it that describe essentially what was in that previous slide, essentially going through. And I didn't go through all of the different definitions of what these things are doing, but I think that would be extremely boring for you. So you can stare at the slide for hours on end and read the definitions on your own if you want. If we were to implement it, it gets implemented. Here's a Java implementation for it with a public interface binary tree. And this is going to be using the iterator from util, as we saw in some of the array examples, dynamic array and linked lists. So we're going to create a method here to return the root elements. We're going to use getRoot in terms of the concept. And then we're going to implement all the different, I don't like this example actually, so I'm going to, next week, actually the following week, I'll bring in some examples, some source code examples, and show you binary trees, just like I did with the linked list and the queues and the stacks and stuff. And I believe your next homework assignment, we'll take a look at that actually at the end of this lecture. It has to do with trees. So I'm going to kind of skip through that code for now, and we'll revisit it next week. In terms of expressions, so we can put expressions in trees. And as I mentioned before, what a compiler does is it takes your programming syntax that you've written in your Notepad file, your .java file, and creates a tree out of the expression, 1 plus 1 is equal to 2 or something. It takes that and represents it in a tree, and then you can solve the math problem by traversing the tree in the right order. So let's look at an example of using a binary tree. So in Chapter 3 we used a stack to evaluate a postfix expression. And now we'll modify the algorithm to construct an expression tree. And it's going to do a math problem, lo and behold. So it's actually kind of easy to explain trees with 1 plus 1. And it's a little bit more complicated than 1 plus 1 is equal to 2, but it's kind of similar. And if you think about the concept, this is sort of like what a calculator is doing when it performs the logic. It takes your expression that you've typed in, and it'll create its own. And this is the other interesting thing, is the tree itself isn't drawn out on a piece of paper in color and stuff, but the structure is created as a data structure, and the calculation to perform on this, to solve this problem, is performed by traversing the tree that's created from the input. So if I were to write a calculator program, and this would be my fancy expression I'd be putting in my calculator's input, I'd parse this input, create the data structure using this input that's going to look like this, and it's going to be a tree representation. Read the tree and come out with my answer. And my answer is going to be correct if I've read the tree correct. So it kind of takes a routine, I don't know if I can say routine, it kind of takes a lot of different types of expressions, makes a generic reading out of it, and allows you to apply that generic reading to solve a problem. Going back to why I said, trees are used for problem solving. So compiler, say this was a line of syntax in your compiling code. It was integer I is equal to 1. It would be drawn out into a tree. Compiler, in one of the stages of compilation, reads this abstract, and they call it an abstract syntax tree, because it's taking the syntax, putting it out abstractly in a tree. It actually creates this kind of tree structure out of it, and it's one of the most classical uses of the tree data structure in programming. And then in a later stage, after the tree is created, we read through it, we apply symbols, we substitute some stuff in for different things in the tree, and lo and behold, we have assembly language that gets converted to machine code, and we have an executable file that runs. Which is kind of impressive if you think about it. It's all built on trees. The entire meaning, the semantic analysis is all tree-oriented. So that's why you learn trees if you want to get into compiler design. Because then you can, figure out how you're supposed to represent the information in a tree. And usually, I've taught actually compiler design before at a different school, actually, but the biggest thing that people still struggle with is they haven't taken data structures, so they have no concept of the tree, and they automatically want to put everything into an array. They want to make a list of all this stuff. They take all these tokens and they put it into a list, and then they try to, represent the list somehow. The concept is, if you're trying to convert this, let's say this is C language syntax, and you're trying to convert it into assembly language. The assembly language representation is equivalent, but it's not given to you in the same words. What does integer I mean as an example? Well, I is a variable name. When we have variables in assembly language, no. We have memory. We can store something, so, and then we have, different architectures to think about in terms of its storage. So we can translate it by the meaning that's obtained by traversing the tree, which is what we're going to do here. If we read this tree wrong, we're going to end up with the wrong answer, essentially. It's going to give us our representation. So our expression tree class, if we're going to implement, and what we're going to do is just going to take and create the tree out of this, from that expression. So the class is going to extend the linked binary tree class. So now we're going to start looking at the Java built-in classes. Because one of the good things about Java is, why reinvent the wheel? It's kind of like, we have implemented stacks and queues by using built-in array packages and queue packages. So we have packages for a linked binary tree. I'm not going to see it today, we'll see it later, but it definitely comes in handy. So the class provides constructors that reference the constructors of the linked binary tree class. Also provides an evaluation method for recursively evaluating the expression tree once it has already been constructed, which is the most important part of it, actually. And so the object itself is going to represent the expression of the tree that's going to be stored in a binary tree format. So here's our lovely source code, where we are going to look at the concept of extending or inheriting from linked binary tree, and I'll have an example of this next week that will be a live one, or the week after I should say. That'll be a live one to show you. So to create an empty expression tree, we're going to create an expression tree. We're going to basically have to parse the input and put them into nodes in the tree, which is essentially what we've done in that last picture that we looked at. The tree was created by the input. They actually call those lexemeans. You parse it means reading it and separating it out into tokens. Those tokens are sometimes called tokens, sometimes they're called lexemeans. In binary trees, they're called nodes. So they're all equivalent language, but it's interesting how the language changes as you apply it to different domains. So But in terms of building our expression tree here, it's going to take a look at the size, and it's going to go root left is equal to going to be the left subroot dot root. I've got root left is going to be equal to null, so it's kind of like, you know, inserting nodes into a linked list in a lot of ways. But this one's going from left to right. So now we have from the left, we're going to go to the right from a certain level, and it's a pre-ordered kind of configuration that we're looking at, and it's going to build it left. This particular example is building it left to right, so setting the node to its neighbor on the right. And each one of the levels are going to be interested in their neighbors on that particular branch, for that particular level. So you're not going to have a case in which the level is obscure or unknown in between. As I say, at A, B, and then that was off of C, and then you had a D over here with E and F, or off of here. Even though you're on the same level, you're still keeping the abstraction, so you know there's a line drawn in the middle for the, or not really a line drawn in the middle, but you're going to keep it separated between the left and the right nodes that branched out in different directions. So I'm going to skip through this code because it's not going to make any sense until you see it live. But the code is actually downloadable from the author's website if you're so interested. So input in the postfix direction, and this was postfixed actually. Building an expression tree from the postfix expression. This was the numbers being a 5, a 3 minus 4, a times 9, and a plus, which is just essentially the way a calculator would actually kind of read the information. Our tokens, and this is kind of like why I was introducing the terminology too. If we were to parse this, we'd create tokens or lexemeans out of it. The tokens are going to be the 5, the 3, the minus, and you know, maybe I can make this a little bigger here. There we go. With a top here. The token list that we're coming out with is the expression, and the postfix puts the operators second, the operands first, in terms of the expression reading. And we can push in terms of the method call for the processing of each space. We can push on a new expression tree 5 null null, which means at one level we have 5 and then the other levels are null. And considering we're fixing it to a 3 depth on each one of the levels, we have a 3 null, which means we're adding a 3, and then we have the operands, the operators of the operator 2 is going to be a pop, operator 1 is going to be a pop, so we have a 3 plus put on the 5 and the 3, so we're sort of building it with the operator as the focus, with the operands attached to it as dependent child nodes from the operator. So the minus is going to work with essentially the, this is written weird, but the minus is supposed to be working, let me just go back down here. I was going to say it's going to be working with the other two sets, but I'm reading it wrong. If it was written out in the other expression, I could probably see the original. But with the 5 and the 3 that are going to be partaking in the relationship with the minus. And then we have the 4 over here, and the 4 is outside of the relationship. Let me go back to my original, actually. Just let me refresh my memory on the original expression so I get the order correct. And they should have just put the original expression out there. Here it is. 5 minus 3 times 4 plus 9. 5 minus 3 times 4 plus 9. So now the 5 minus 3 makes more sense. If you separate out the tokens and put them in the order in which the tree is going to be built, you get that string that's on the top of that slide up here. Hey. Oh, yeah, there we go. So that's 5 minus 3 plus times 9 plus 4. Times 4 plus 9. I probably should have written it down. A lot of good that did. Anyway, continuing on. 5 minus 3. We got that 4 that comes in next. The 4 is on a different branch node. Is it going to be times 4? Yeah. Yep, times 4. So we have the 5 minus 3. So if we collapse that down, it would be that times 4. And then we're going to do a minus 9 on the end of it. So we're going to, we still got the lonely 9 out here. It was at the end. Or is it going to be times 9 or something? Well, we'll see here. It's plus 9. So 5 minus 3 times 4 plus 9. So we're reading it from a postfixed in direction from bottom up in terms of and putting the operands first and the operators second in terms of the order in which we're building the tree. So we would have to read it that way, long story short, in order to actually solve the math problem correctly. Otherwise we get the wrong answer. We all know the order of precedence. So usually we order the precedence, order the tree in terms of the precedence. So. In terms of the postfix and the postfix evaluator classes, there are modifications of it that are presented in Chapter 3 earlier using a different structure. I'm not going to worry about it. In fact, it was probably used stacks, which is probably what the second bullet point is going to tell us. Solve the method, yes, using a pair of stacks to create the expression tree along with a valid postfix expression. So then outputs the results using the evaluator method of the class. So I'm not going to go through the evaluator method of this class either. So I'm going to skip through that. That's why the slide set's like 80 slides long. I probably could get it through it today. There we go. Here's the, that's because I'm going to skip half of it, because I'd rather just show you my examples instead. But we're just basically trying to go over the concepts today in terms of the vocabulary and everything. Here's the UML expression, UML diagram that would be used to express this equivalence in terms of the implementation. A linked queue, maybe with a binary tree, and the binary tree is going to have a binary tree node that's going to be part of the tree. And then we're going to have a binary tree interface class that's going to give us the interface for the nodes. And then the expression tree, and then perhaps being used in terms of a postfix evaluation to evaluate the tree so we can get the operand, get the next token, kind of methods that would be part of that. And then some data structures to keep track, the linked stack to keep track of the components that we're working with. Because even though we've actually put it in a tree, in terms of our analysis of what we're trying to read and the problem that we're trying to solve, and it's represented in a tree formation, it doesn't necessarily mean in solving the particular problem. Let's say, for example, we wanted to read it and implement a calculator from it. We could still use stacks, actually, because we pop on, which is essentially what the runtime environment does in an operating system. It uses a stack to keep track of the instructions, reads it, builds it, reads the logic, and push 5 on, push 3 on, push operator minus, oh, okay, evaluate that to 2, 5 minus 3, and then push that up, take it off the stack, pop it off the stack, push on the next one, push on the next one. So we're kind of implementing a tree for which when we're reading the tree, we're also supporting stacks and other data structures that are working with it. And I'm hopefully going to show you an example of this next time. That it's going to essentially use multiple different types of data structures, which is why trees come last in the data structures course, because then you can build a tree structure application that uses a stack and a queue and uses all sorts of other little things, linked lists and stuff. That kind of builds on the concept and kind of adds a little capstone to the data structure concept. So, in terms of implementing it with links, we're going to examine the next example here, and I could probably get through this. It's not going to be that long. In fact, there's only got like 20 slides left, and half of it's source code examples. So I'll finish this whole lecture today, actually, which would be good. So examining the linked list implementation in terms of the binary tree example for our implementation, you can keep track of the nodes. That's the node, the root of the tree, as well as the count of the elements in the tree. So we have the counter here, as well as the loop. In terms of the linked binary tree, you're going to provide 2 constructors for this. One to create the null tree and empty tree. The other one is going to be basically creating a tree containing a single element. So we can create the tree in terms of the constructor. Empty will create an element. And this code is going to kind of give you an overview of how to create the structure, implementing it with nodes, essentially. Now I'm not going to, as I mentioned before, I'm not going to go through it, but the concept itself is fairly similar to the linked list structure, actually. So you also need a class to represent each one of the nodes in the tree. Just like you can create a node, you can create a list, and you can create the linked list. You can combine the 2 structure. So to represent the nodes in the tree, you're creating the tree, and then you're creating the node. Essentially, it works with it. So since it's a binary tree, you're going to create a binary tree node class that contains a reference to the elements stored in the node, as well as references to each one of the children. And here's an example of the binary tree class that you'd create if you're going to put one together. So, So looking at some of the other methods for the binary tree class, and these are generic, keeping in mind each node of the tree represents a subtree. You can find the method maybe providing an excellent example for recursion. So you can actually apply, which we have talked about already in this course, the concept of recursion. We could apply that to the nature of traversing the tree. So if we know all of the levels, we can actually have a controlled situation, because when we hit the root, then we stop the recursion and we come back down and we supply all the missing values after we've read the entire tree nodes, branches. So we can use private methods to find, again, support for the public find methods itself in terms of the implementation details. It may also allow you to distinguish between the original invocation of the method and the subsequent recursive calls as well. So here's our and I'm not going to go through this again, but a little sample in terms of implementing the find feature using a recursive type of solution for it. And recursion actually works quite well for trees because it is such a controlled environment. And the one main problem with recursion is, when we looked at it a couple weeks ago, was that issues of it being uncontrolled, issues of it filling up this runtime stack, getting Stack Overflow errors, running out of memory, not working properly in terms of, it's not like a loop. A loop isn't going to be allocating every time you go through a recursive call. So it's great, in terms of using a loop instead of recursion for a lot of simple things. But in the case of traversing a tree, the recursion actually makes a lot of sense, because, does it have a parent? No. Then you stop the recursion. So how do you know how many parents are in the tree? You don't know. So it lends itself quite well, because you can loop it without knowing how big the tree is, and you don't have to change it, you don't have to fix the size of anything. And it's kind of like a while loop, essentially, but you're implementing it with a recursive call to a method or to a function that's going to check the value of something, it's going to evaluate something, put it into a stack over here, put it into a stack over there, and then go back up a level, and then go back up a level, and then go back up a level, because all the nodes are the same, essentially, in terms of the recursive call. Anyway, we could also implement an iterator if we wanted to. We have the iterator in order method. To find a method, the iterator in order, basically the method uses a private method in order to support the recursive call. In terms of the private method, it's not necessarily, it's more of an implementation choice. It doesn't necessarily have to be done that way. So traversal of the tree might be implemented using a two-string method example for the iterators, or both. Maybe a two-string might be put in there to convert the values. So, and this is kind of like why I don't like the example. It's such, it should be done this way. It doesn't necessarily have to be done this way. It's one of the common types of implementations of the concept. So looking at an array element of the binary tree in terms of implementing binary trees with arrays, implementation is going to keep track of the array containing the tree, as well as the count of the elements in the tree, because we have to keep track of the count so we can build the array of the right length, which is one of the issues that we have. So, in terms of the array, the array binary tree, we'll provide two constructors in terms of its, using in the array implementation for the binary tree. In terms of its implementation, it's going to be the same constructors as we had in the last example. One is going to be null, the other one is going to add a single element, or we're not going to call it a node, we're going to call it an element, because we're not creating a linked structure. But the concept is practically identical. And we'll see an example of this as well next time when I run through the source code examples. So looking at the methods of the array binary tree class, so like in terms of the linked implementation, keeping in mind that each one of the nodes of the tree represents a subtree, which is kind of the interesting concept. We wouldn't actually know that. We wouldn't actually be paying attention to that. It could just be a list item. Except for the fact of what the data that we're storing at one of the positions. It just is more complex than a single data value. It's a multiple data value. So, implementing the find, kind of be the same. So, in terms of the iterator order method, it's going to be very similar again as well, just like the linked list example. So the method, the private method of the in order to support the recursion is going to be, the example is actually identical. So traversing the tree might be implemented as well as using a two-string method. So, which is kind of like why I don't like the author's examples, is because they're really all the same. and they're presented over and over again. So let's take a quick look, because I do have a few minutes. Let's not install any updates right now. Let's take a quick look at that assignment that I'm trying to envision that uses trees. I can't imagine me not giving you an assignment that doesn't use trees. So I want to say it's the last assignment. I want to say it's number 4. Nope, number 4 uses heaps. Did I not give you an assignment using trees? Nobody knows. Nobody knows. Let's take a look at 3. I did. Binary search tree. There we go. I knew about it ahead of time. I just couldn't remember what number it was. People looking at me like, did she? No, you're going to take a data structures course and you're not going to have to implement a search tree. Nothing about trees at all. Although I am going to talk about it. Yeah. Assignment number 3. And you should be working on assignment. We only have 4 total. So, the English language is made up of 26 characters. Or letters, I should say, if I read it correctly. These letters are made up of words. So we got words, characters. Well, one usually does not say one word is less than or more than another word. One could view a word that appears before another in a dictionary, alphabetical order, is less than that word, and a word that appears afterwards is more than. We consider a sort order of alphabetical characters. By this definition, identical words are the same. So parsing a file that you read, so you're reading a file and it's going to collect information about the file. So in this assignment, you will parse a file and put all the words in a binary search tree. You're going to take the file, take the words and put it in a binary search tree. You're going to use the binary search tree to collect data about the number of times a word has been found in the file. Well, you're going to read it in, so you're going to be able to do the count at that point. You should make no assumptions about which letters are in the middle, like M. The first word you encounter will be the roots. If the next word is greater, then it will be to the right. If the next word is less, then it will be to the left. If it is possible that the tree that you make will be very sparse, think what might happen if the first word is zebra. You're at the end of the list. There's nothing you could put on the tree, essentially. Assume all words in the file are lowercase, and you can certainly rig your input to create the tree that you'd like to create. This is definitely something where you can mess around with this text file. I'm not going to give you. It would be worse if I gave you the text file. You can mess around with the text file and make it work properly. Assume all words are in the file are lowercase, or convert them to lowercase if they're not. I recommend using a string library, string class. It makes comparison much better. You can just do is this one greater than? Actually, it'll do a greater than or less than. It tells you, returns. After you've located the file in your binary search tree, the user should be given a chance to type a word, and the computer should say the number of times the word was found in the file, 0 or more. So if it's not in there, it would be 0. If it was in there twice, like the word the, as an example, if you wrote a couple of sentences, the dog ran down the street, that would be 2 thes in there, So implement the above program in any programming language that you want, and it meets the requirements as described above. So you're building a binary search tree with a bunch of words, ordering them in their alphabetical order, essentially, in terms of, and you're keeping track of how often they appear. You've got a list. So this list of this count can be an array. And say, for example, you'll say you've read the file in and you say, oh, I got 10 items. And for my 10 items, I can run through all those items again and say, how many times, like the first item can be item 0, second item could be item 1. How many times is the? Well, the was the first item, actually. It appeared twice. If I were to think about that sample sentence I just gave you. The dog is just once. Ran once. Down once. That's a repeat. There, we don't have to put the in there again. We just increment the count to 2. Street, 1. And we build a tree out of that. And so the customer or the user comes up and says, types in the. And you go check the tree. And say, well, is the in there? Oh, there it is. There it is. Found it. 2. And user input comes back, the output comes back to the user and says, that was in there twice. Sounds kind of simple, doesn't it? We'll see next time. I'm gonna try and remember. I have an example that actually builds the words for you, but I'm not gonna give you the whole search. So think about it ahead of time. Tackle it if you want. Next week there's no class because I'm going to be out of town. But the following week we will be going through some examples that will go through that. And that last assignment was on heaps, huh? So we still got more stuff. So we still got about another month left. It's only the beginning of November. So we still got another entire month of November left. Although we have holidays coming up. But we'll get through all this. So questions, comments, or concerns from today? You guys like binary trees? Trees in general? All right, well, we'll see about that. We'll revisit this concept next time. All right, thank you.